Let's now explore a little bit of the wave nature of particles. Louis de Broglie had a hypothesis, and this hypothesis was this. So he took this was a well-known equation that related the momentum and the wavelength for a photon, and he took it, solved it for wavelength here, and postulated that it holds for any object with momentum, not just a photon, an electron, a nucleus, an atom, a baseball, whatever. And therefore, you should be able to see interference and diffraction for material particles just like you do for photons. And to de Broglie, relativity demanded symmetry between matter, particles, and energy photons. E equals mc squared treated both of these things on equal footing, and so this was sort of where he came from with this. But it's important to say that there really wasn't any evidence for this whatsoever, and so this was really a remarkable idea. So we mentioned this was a well-known equation for photons. Let's just show where this comes from. So if we take our relativistic relationship for energy and look at this for a massless photon, we get E equals Pc. Of course, we know from the photoelectric effect, here's how we get the energy for a photon in terms of the frequency. And basically, we just set these two equal to each other and then use the relationship for the speed of light, wavelength, and frequency. And together, if you go through, you can solve for this relationship. So again, this was understood for photons, but the big jump here was to use this for massive particles. So once again, this means that in theory at least, one should be able to do interference-style experiments with massive particles like electrons and protons. And so here's the slide from the two-slit interference we looked at a little bit ago. And with the equation. So we should be able to do this, and so we're going to need to go back and use this stuff when doing some of these problems. And so here's a clicker question. A beam of electrons and then a beam of protons are shot through a double slit with a very small slit spacing. The electrons and protons travel at the same speed. Which is true about the interference patterns caused by these particles? So maybe go ahead and pause here and think about this one, and we'll talk about it. Okay, I got A. And you can reason through this of both these equations here. So the two particles are going to have the same speed. However, the momentum is going to be different because, right, the mass of a proton is much bigger than the mass of an electron. And so the bigger the momentum, the smaller the wavelength from the de Broglie relationship. And so what that means for us is the wavelength of the proton will be smaller in this case than the wavelength of the electron. And then from our equation here for two-slit interference, the bigger the wavelength, the larger the theta will be because the d has to remain the same in the n for the different fringe that you're talking about. And so the theta is bigger with a bigger wavelength. And so since the wavelength is bigger, it'll be electrons will have the larger fringe spacing. And physically what this tells us is that electrons will be much easier to do these type of experiments with in general, everything else being the same, because they'll typically have a bigger wavelength, if everything else is the same. In 1923, de Broglie proposed this, that particles have a wave component to them. And in 1927 was the first experiment which showed this wave phenomenon. All right, and so this was a diffraction experiment. We'll talk about this in a second. Later, more recently, Young's two-slit experiment has been performed on electrons. Again, this is an interference wave phenomenon. And basically, interference consistent with the de Broglie relationship has been seen with all sorts of particles, electrons, protons, neutrons, atoms, and molecules. The book has a really good section on this. I definitely encourage you to look up some of these experiments. They're very interesting. But what really seems to be happening is things that we would call particles do exhibit wave phenomena. And this can only really be explained if they have this wavelength, as de Broglie hypothesized. And so here's the diagram of a simplified Davisson-Germer experiment. So I just wanted to run through this. And basically you have a beam of, in this case, were neutrons coming down and hitting on a surface. And so here's two atoms separated by some distance d. And what you do in the experiment is you just go around and try to see which way these particles are reflecting off. And so, for instance, let's say there's a reflection over here this way. Now what the experimenter literally does is they measure the angle of where there is a peak, okay, where these particles seem to be reflecting off of. And the idea here is that if they do exhibit wave phenomenon, you can think about this as being sort of the first beam and this being the second beam. And so these two beams will meet up somewhere, off in this direction, and at the particular angle where there seems to be a reflection is they're interfering constructively. All right, and so if we look at these two beams, so again, beam 1 and beam 2, the quickest way to look, again, what we're interested in when we talk about this kind of stuff is the path length difference. And so if I just draw a line here connecting this beam to where this beam starts from at a 90-degree angle, roughly, this right here is the path length difference. This is the length that beam 1 travels more than beam 2. If we just look at our little diagram here, all right, we've got a little triangle. This is the right triangle here, and so I'm trying to find this sigma, and so this is our angle theta. Well, if you look here, this should be our angle theta as well. All right, and so if I just use my right triangle here, I can sort of blow it up here to make it look a little bit easier to view. So there's the right angle. I'm trying to find this sigma, and here's my theta, and here's my capital D. And so my sigma is just going to be d sine theta. And so what should happen then, in this case here, is when d sine theta equals an integer number of wavelengths, you're going to get a constructive interference. And this is in fact what they found. So the book goes through and does a little bit of a calculation here, but that's the background of this. Let's try an actual calculation here. So here we're doing a two-slit experiment with a beam of electrons, and they have a wavelength of 0.1 nanometers, and they're going through two slits that are separated by 10 nanometers, and the screen is 1 meter from the slits. And so this is going to go back to wave stuff we've talked about previously. The question here is, what is the order of magnitude of the distance between bright spots of the interference pattern here? So give this one a try, and we'll talk about it. Okay, so I got A for this. And so let's go back. So the equation we're talking about, our two-slit interference equation, is this. D sine theta equals n lambda. And we're going to use the approximation, which is almost always going to work for us when we're dealing with things like electrons, very small wavelengths, this right here. And so what we're interested in this y. If you remember when we talked about this, so we're going to have our bright spot at some angle theta. So here's a bright spot, and this y is the distance from the center up to that bright spot. Big D is the distance from your two slits to the screen, and so everything on here is what we have. And so I'm interested then in this y. So y for us equals n lambda big D divided by small d. So if I plug in our numbers here, our wavelength is, 0.1 nanometers. And we're dividing by little d, which we said was 10 nanometers, and then multiplying by the capital D, 1 meter. And so when I do this, I get n times 0.01. So basically it's n times 1 centimeter. And so if we look here, let's do the first peak. When n is equal to 1, we get 0.01 meters, so 1 centimeter. And then our next peak would just be 2 times that, so 0.02. So in the case here where you can use this approximation, the distance between these peaks is the same, and so you can do this rather quickly. So basically the first peak comes at 1 centimeter, the second peak 2 centimeters, so overall the distance between them is 1 centimeter. And so this is important that you can sort of connect this stuff from first year and use it here with these electrons. Let's focus on the two-slit interference experiment that we've been talking about here with a particle. Now, in the textbook, Moore defines a quanton as some object that obeys the laws of quantum mechanics. And so what this really does is it kind of blurs the line between, say, a photon and an electron, which is really what we're doing. So when we talk about this experiment, we can talk about it with using photons or electrons, and so he'll just call a quanton. So when we do the two-slit interference with at the particle level like this, what happens is the quanton arrives as a clump, and we can see that over here in this picture. So what will happen is the quantons will start to arrive as little clumps over here. And it's impossible to predict where it will land, so it seems random. However, as more and more land, and so you see here on this picture, this is the exposure time. And so as more and more land, you see a pattern emerging, and you get what is basically our two-slit interference pattern. And so the arrival of the quanton is very particle. It arrives as a big clump. However, in order for this pattern to arrive, this probability has to be a wave type of thing happening. So you have two different models, the particle model and the wave model. And you need both models to describe the experiment. And in fact, you can ask this question, does it act like a particle or does it act like a wave? And what it is it transcends this. All right, so it's something different that we don't really have language for in classical physics. And this is summarized in Bohr's principle of complementarity. So Niels Bohr is going to be really big in the development, as we'll see, is really big in the development of quantum mechanics. And so what he says is you need these two different models in order to explain what's happening. But of course, what's happening transcends both of these models, and that's going to be the part that's really weird. So let's talk about this. First of all, this is very non-Newtonian, right, that this happens, because we're using these two different models. In regular physics, we have particles, we have waves, and they never sort of match up or have to be used together. And we have this idea of this seemingly random behavior with an underlying order. And so let's just think about one hypothesis that you might have. So maybe the photons are interfering with each other. And so what people have done is they've done this with one photon at a time. So you can do this experiment where you basically slow down the emission of the quantons, the photons, or the electrons, whatever you're talking about. So basically only one is going through at a time. And so Dirac has a really famous quote, each photon interferes only with itself. Interference between different photons never occurs. And so in order to get this pattern, we know from the stuff we've talked about that this is the equation here that this basically defines this pattern, right? So D would be the separation of the slits, and the theta basically tells us where each of these little bright spots is going to be happening. All right, and so Moore talks about this, that, okay, when you're doing this experiment with an individual photon, each photon must know about the slit separation. And this is a really weird idea, especially this idea that the photon is cognizant, but it's just a colloquial language here. But basically, in order for this to happen, the photon needs to have some sort of information about this slit separation. All right, and a particle can't go through both slits. A wave can, and so this is the problem. How is this particle, all right, how does it know about the slit width? And so the classical models break down at this point, and Moore has a nice discussion of this and basically ends up with a good quote. It's just something we will have to deal with. So I think a lot of people at this point get really confused, and they want to sort of be able to make an analogy to something they have experience with, and there just is nothing that we have experience with that works like this, and that's why it's very weird. Now, what you can do is to even kind of press this point more is to really try to seek trajectories. And we add what's called a proximity detector. All right, so this basically just tells you if the quanton, the photon or electron is near it. And so it's basically a way to actually figure out which slit that your quanton is going through. And this has actually been done experimentally, and it works. Okay, when this happens, only one of the detectors goes off at a time. So here's our detector. So when you do this, like, only the top one will go off or the bottom one will go off, and so it'll appear like, oh, okay, it went through the top slit, it went through the bottom slit. The problem is when you do this, it destroys the pattern. Okay, so instead of having a nice interference pattern, you get basically a pattern where there's a whole bunch, the ones that come through this slit just sort of pile up over here, and the ones that go through this slit pile up over here. This is sort of the probability of where they'll land. And so you don't get these interference effects. And so the rule here, and we're going to see this again, is that if there is no way to tell which path your quanton takes, an interference pattern will emerge. If there is a way to tell, the interference will be destroyed. And so this is really weird, another really weird thing. The conclusion here is that it's just not meaningful to talk about trajectories. First of all, they're nonsensical. Okay? If the particle did go through one of the other slits, it has to somehow know where the other slit is, which doesn't really make any sense. And so that's a really weird thing to think about. And then finally, if you actually measure what the trajectory is, it changes the results. Now, we will say that this is tricky. We'll talk in class a little bit about, so this brings up ideas about the interpretations of quantum mechanics. And so people interpret these things differently. We'll talk a little bit in class about this, but really there is no defined way to interpret this. And Just a little thing here that I like to talk about sometimes. They did a contest recently where they tried to summarize quantum mechanics in 5 words, and the winner came up with this: don't look waves, look particles. And you can really use this, I think, in a lot of cases this semester to help. And so like in this case, if we don't look, if we don't try to figure out which slit the particle is going through, it behaves like waves. We get a really nice interference pattern. If we do look, okay, we actually find that they went through one slit or the other, but of course then it behaves very particle-like and we do not get the interference effects.